Okay, thanks. So today I'm going to be talking about NPR, or noise power ratio. So what is it, how can I simulate it, and how can I measure it? So I'll start by talking about what NPR is, before showing a couple of approaches that you can use to simulate it and to measure it. Then show you the measurement setup that we used in our lab to measure a couple of amplifiers before presenting the results, and then comparing those measured results with simulation to see the fit, before summarizing at the end. So noise power ratio is a figure of merit for the linearity of RF and microwave amplifiers, particularly power amplifiers, and it's most appropriate for wideband, or those that will operate with wideband multi-carrier signals. So a typical NPR test signal is shown in the figure on the left. The notch is a bit wider to make it clearer, but you have band-limited white noise with a narrow in-channel notch, typically much narrower than the bandwidth of the channel. And this is a more representative test signal than the two tones that you might get in an IP3 measurement. And so it gives you an idea of the in-channel distortion from multiple carriers on neighboring channels. So when this is fed into an amplifier, the non-linearity of the PA produces intermodulation tones that then fill up that notch. And the noise power ratio is the noise power ratio is the ratio between the channel power density and the power density inside the notch. And then this is commonly plotted as a function of the PA's output power or power backoff. Noise power ratio is quite an old, or it's a metric that's been around for quite a while. Originally for I think FDM systems, but more recently it's used in defense and SATCOM applications. So there are a few different ways that you can simulate NPR, and in this presentation I'll show two. The first replicates the traditional measurement setup shown on the top. So you have a noise source, and then you filter that to generate your signal, which you pass into an amplifier. And then the second approach replaces that noise signal with a multi-tone source, which is maybe a bit similar to the multi-carrier signal that would be used in practice. So for the first method, we generate a noise. So this is the schematic shown is adapted from a Keysight example, noise power ratio simulation using envelope. And the noise signal is generated with a voltage source and an IQ modulator. And then this is passed through separate band pass and band stop filters to create the band limited signal and create the notch as well. So there are multiple parameters that you can adjust here if you want. So you could adjust the IQ modulator settings, or you could adjust the filters, but it's generally good to go straight away. You just need to replace their amplifier with your amplifier. The other parameters, they have some effect on the performance, but it's not major. So for our simulations, we mostly just kept them as they were. And then this plot shows the spectrum of the output signal from the amplifier. So you can see that at low, or as the power is swept, so you can see that for low powers, the ratio between the channel and the notch is quite big. The amplifier is operating mostly linearly. So there aren't that many tones, but as the power is swept, the notch fills up quite quickly as those intermod tones are generated. So then this shows the alternative approach that we used, where the noise source was replaced by multiple CW tones, sort of approximating a more realistic signal. And then the phase of these tones was randomized to avoid them summing in phase and causing excessive peak to average power ratios. So it's a much, it may not look it, but it's a much simpler setup. You just have all the tones on the left-hand side with just different blocks in ADS to create them. So lots of current sources going straight into the amplifier. And then this again was this was adapted from a Keysight example workspace from the Knowledge Center if you wanted to try it yourself. Yeah, this uses the harmonic balance simulator, whereas the other one used the envelope simulator, which if you have licenses for everything might not make a difference, but this is maybe a bit more accessible if you only had access to one. And then this shows the this shows the spectrum at the output of the amplifier. Again, you see quite a big notch depth at low input powers, and then as that power is swept, the notch fills up quite quickly, and the noise power ratio decreases. You may be able to see inside the channel. There's quite a large range on the arrows. There's quite a large range on the arrows. So we need to run multiple simulations and then multiple simulations that we can average this to get a more realistic reading, which we do using the Monte Carlo block. So for this is the result of 25 simulation trials and 1,001 tones, I think, which we found gave us a reasonably good fit with the measurements. I think the simulations tended to take a few hours, so we didn't want to go beyond this. But if you wanted to, you could maybe get more realistic results. Just briefly to compare the two. So when we simulated amplifiers, when we simulated these on amplifiers, we got similar results for both in terms of the trends. You'll see those results later when we compare simulation and measurement. They didn't match up exactly, but for the sake of designing, we thought the fit was fairly close. The multi-tone simulations ran considerably faster than the envelope noise simulations, by a factor of about 8 to 10 times. So the multi-tone simulations might take 2 or 3 hours to run, but then the envelope simulations we were having to run overnight. So it wasn't quite as practical to do those. Though that was that does depend on how many Monte Carlo trials you run. So if you need to run more, that gap closes. And then that also was the case for the PDKs that we used in the EM models, but it's possible that might not always be the case, but yeah. Yeah, and then as you'd expect, it was time consuming to simulate at higher bandwidths for both approaches. So you have sort of a trade-off between speed and accuracy, whether you take that by adjusting the simulation settings or by adjusting your schematic, maybe converting some of those EM blocks to PDK elements. But yeah, you can't have both. Okay. So those are the simulation approaches. Then, as designers, at some point we're going to want to measure the amplifier, and then there are a few different ways that you could do this. We've shown a few here. So there's the traditional way, again, where you use a noise source to generate white noise, bandpass filter to set the channel bandwidth, which is typically the full bandwidth of the channel under test, and then a separate band stop filter, typically much smaller, and that's maybe about 1 to 10%. That's what we found in practice. So then that goes into the DUT, and then you measure the output on a spectrum analyzer to check the channel power and the notch power. So yeah, typically that was done with separate elements, separate noise source, separate filters, which is cost effective if you're always operating at similar signal bandwidths and similar frequencies. But if you have different frequencies, different amplifiers you need to test, it's not very flexible. But sort of more recently, you have signal generators that are capable of generating the full NPR signal. And that can be a noise signal, as you kind of see there. That could be a multi-tone signal, like we saw in simulation, or some signal generators will generate the full modulated signal and create the notch for you. So if you wanted more applicable NPR results, you could do that. Though that wouldn't, strictly speaking, be NPR, and it wouldn't quite be as generalizable. But you have that option sometimes. So yeah, when you're measuring NPR, there are some limitations at the low end and the high end. On the low end, it's the thermal noise floor of the spectrum analyzer that sets a limit. So when your amplifier's quite linear, the intermod tones are a long way below the noise floor. And then as you increase the signal power, the gap between the noise floor and the signal power increases. But technically, you're not measuring NPR at this point. So this increases linearly until you get to a point where the intermod tones are equal to the power of the noise floor. And then we get the peak NPR, which should actually be a peak ideally. And then at this point, this is your first NPR measurement. So then further increasing the signal power, the NPR will decrease as the notch fills up. As the notch fills up. And then on the high end, the noise power ratio could end up being limited by nonlinearities in the mixer, in the spectrum analyzer, so generation of intermodulation products in there, which you can sort of combat by adjusting the reference level to its optimum, the reference level and attenuation to their optimum levels. Or you can have overload of the ADC or the IF path inside the spectrum analyzer, which is what limited our measurements. Okay. So this is the measurement setup in our lab. On the left-hand side, we have a signal generator. We had an SMW 200A from Roden Schwartz, which can generate a noise signal, multi-tone signals, and some modulated signals. But for this work, we only looked at a noise signal. So yeah, that generates the signal, which goes into the DUTs on the heatsink on the right-hand side. And for this, we looked at a couple of PAs or a couple of amplifiers. They weren't designed with noise power ratio in mind, but they were tested to show the measurements. So we have the A702 is a 28 gigahertz gas PA, and the B701 is an 18.5 gigahertz gain block designed by PRFI. And then the output signal from these amplifiers goes into the spectrum analyzer in the middle, an FSW50, which measures. It calculates the NPR automatically, but you can take separate measurements of the channel power and the notch power and calculate it yourself. The instruments can be connected if you want to make sure that any changes on the spectrum analyzer are reflected on the signal generator, so that the signal you're generating is always aligned. But in practice, we set custom notch widths and channel bandwidths to align more with the settings that we had in simulation, which weren't quite the defaults. And then briefly, we took measurements over a lot of different frequencies, channel bandwidths, notch widths. So we automated these to speed up time. And this just shows like the setting screen before our measurement sweeps will be set, sweep settings, and then settings on the signal generator and the spectrum analyzer. Okay. And then this is what some of the measurements look like in practice on the spectrum analyzer. So again, the notch starts off quite deep, and then as the signal power increases, it fills up, and the NPR reduces, in this case from, I think, about 32 to just under 20. And then I think by the end of this sweep, it sort of passed 1 dB compression. And you can see the power densities of the channel and the notch, which are used to calculate the NPR. I don't know if at the back you can make out the vertical green lines and blue lines. They mark the notch width and the channel bandwidth that are set. I think these are the default settings, but we adjusted them slightly to bring the notch in, and I think we shifted the channel bandwidth slightly, so it's more like the settings in the Keysight test benches. So these two plots show NPR measurements of the A702. So on the left-hand side, we have, these are just under two conditions. So on the left-hand side, we have a constant notch width, and then we vary the channel bandwidth from, I think, 50 megahertz to 1 gigahertz. And then on the right-hand side, we had a constant channel bandwidth, and then we varied the notch width from 1 to 10%. So we see the best consistency for the constant notch width, constant channel bandwidth, which we kind of expect if the nonlinearity of if the IMD tones generated by the nonlinearities of the PA are caused by the input signal, we have sort of the least variation of the input signal when the notch width is varied slightly, whereas when we're varying the input signal from 50 megahertz to 1 gigahertz, we'd expect the nonlinear tones generated to be different. Yeah, you can see the variation there. And then with the B701, we saw similar trends across these plots, but also across the other measurements we took. So good or reasonable consistency across constant notch width, but then more variation across different channel bandwidths. Yeah. Yeah, what we were most interested in was the agreement between simulation and measurement, which you can see here. So for the A702, the blue line shows the NPR measurements with a noise signal. The green line shows the simulated NPR with a noise signal, and the red line shows the simulated NPR with the multi-tone signal. So they both follow, both simulations follow the trends of the measurements, but you can clearly see they don't follow them exactly. So we sort of need to bear that in mind. Overall, we think it's a reasonable fit to help us when we're designing. We'd be sort of reasonably confident, but we wouldn't want to quote sort of exact numbers. And then in this case, or in most cases, as you'll see, the multi-tone measurements align more closely with the measurements. The noise signal, we see increased variation at all powers. We think we'd be able to address this through adjustment of the simulation settings and with more averaging. But the simulations took so long to run that this wasn't feasible to do. These were the simulations that we had to run overnight. Okay. And then with the game block, we saw sort of much better agreement between the multi-tone signal and the measured NPR signal. They sat on top of each other. This is just for one case, so 50 megahertz, 10%. But we saw similar results across different bandwidths and different notch widths. Again, the noise signal, there's a slight offset. It doesn't quite agree with the measurements as well, but we think we could address this with sort of more simulation averaging. Also, just stressing, this is the case for 2 PAs that we've measured and sort of 2 gas PAs using a certain PDK, and this might not be the case for all amplifiers, all simulations. So yeah, you'd need to try it yourself to confirm the way that it works for you. But yeah, that's sort of quite short, but that's in summary. NPR is a linearity metric for amplifiers with multi-carrier wideband signals, increasingly seeing in SATCOM and defense sectors. There are several ways to measure and simulate it, but the 2 most relevant ones that we see are using a noise signal, like is traditional, and then using a multi-tone signal, which has advantages in simulations. We find the increased simulation speed means it's probably more convenient when designing PAs, though sort of we wouldn't want to make this claim without sort of trying it on more amplifiers, more processes, things like that. And then we see what we consider to be good agreement between the simulations and measurement. They don't line up exactly, but we'd be reasonably confident when designing things for ourselves that the measurements would turn out okay. Just thanks to Keysight for their support with the example workspaces and test benches, and then Roden Schwartz for their support with the measurements. If you'd like more information on any of this, we have stuff on our website. We also have a YouTube video with Rob Smith there, who contributed to this paper, if you're interested. But yeah, thank you.